When you redo it, set it like we were just all discussing. So, pull everything around, make it a negative x equals 2 equals y, and y equals 0. So I punched all these guys in just to get an idea, because I already had an idea in my head anyways. But now, when I'm looking at it, I see that, you can probably zoom in if you want, but there's an area where, okay, so the 0 is our horizontal floor, and the parabola is going to come through here. So you want an area that's defined by all three functions. It's just this little piece right here?
Yep.
All right.
That's it. Okay, I'm gonna go through this. Let me suggest something real quick. Those aren't the curves we're given. I've taken, everywhere I saw x, I switched it to y. Everywhere I saw y, I switched it to x, right? That's not what we're given, but I just want to see, could we graph this without a calculator? Do we know what x to the fourth looks like? Yeah. It looks like x squared, but it's a little bit steeper, right? It goes up a little sharper. So it's going to look something like this, right? It's a parabola-ish looking thing. And then how about this? It's a square root function, right? But it's been kind of moved around a little bit. Well, let's try and find a point that definitely lives on that. Let's try and make the whole thing inside 0. So x is 2. Do you agree? I'd be 0 here, right? Give me another value of x that I could plug in there that would give me a nice output. 1 would work? Yeah. If I plug in 1, I get what? 1? So up here like that. What else would work? 0? 0 would work? Right, 0. Yeah. I could plug in 0. Could I plug in negative 1? Negative would become plus, right? But I couldn't plug in 3, could I? No, because I get a negative under the root. So it would be like this, wouldn't it? Something like that? You could just switch the variable? No, I'm just trying to see, could you graph it if it were the other way? Could you? Yes? You could? And then instead of, now this is important here, instead of y equals 0, if I'm going to go with this same mentality of switching the variables, I should be looking at x is 0. Where is x 0? The y-axis. The y-axis, which is actually this, right? So what's the region bounded by all three? That little area. Right there. Right in here? Yeah. What about this? Right? This right here? But this, you know what? I remember this problem. I forgot to put a greater than symbol. I never saved it when I redid it. Y is greater than or equal to 0. Okay, change that to y is greater than or equal to 0. And that'll change it to this stuff to the right. X is greater than 0. That okay? Now look, this is if it were that. That's not what it is, right? So let's try and draw that now. All right? Let's try and draw that. You can do it the same way without a calculator. First thing, sideways parabola. The whole thing. Nope. See, that's the problem if you solve for x. That's the problem, is that you run into an issue there. If you do this on your calculator, if you solve this for x, which means you took the fourth root on both sides, your calculator is not going to draw the bottom half. And that's a problem. Now the other one, we just said, wait a minute, y. We just said we could get this to be 0 if we let, this time, let y be 2, right? And then we could also let y be 1. Understand? And you would get, yeah, but it goes like this, right? And then y is greater than or equal to 0. Where's that?
Above the x-axis.
It's above the x-axis and above, right?
Yeah.
So what's the region bounded by all three? This little piece in here. Is that what we had said? Okay. What? It didn't because y was greater than or equal to 0. But had that condition not been there, right? Had this not even been part of the problem, then the region we're talking about is this entire region, and then you would be in trouble there because you'd be missing that whole piece. Are we good with this? Okay. Do you want to do this with vertical rectangles or horizontal rectangles? Vertical?
Oh, yeah, no, horizontal.
Vertical would change, right? Wouldn't they? It would change. Not to mention, these are functions of y already given. If they're functions of y to start with, then you probably should be thinking horizontal rectangles. So I'm thinking our rectangles should go like this, right? And now I'm going to take a look at that rectangle over here. Here's my y-axis. My rectangle is in there like this. Which function creates the boundary on this side?
The square root of 2 minus y.
Exactly. This is the square root of 2 minus y. Which function creates the boundary on the left side? Y to the fourth. Right? This one right here is y to the fourth. Do you all agree with me?
Yes.
Okay. I kind of drew that backwards. Yeah, sorry. Sorry. This one is more like this piece. Doesn't really matter how you curve it. It's just, which one's on the right, which one's on the left. Understand? That's this little blown up over here. Okay. What else do I need? I need the endpoints, the limits of integration. And since I'm doing this with a horizontal rectangle, it's going to be y values. So what's the smallest y value? 0. And then the largest? It's where they hit each other, right? Which is, you're saying 1, and you're getting that how? Setting them equal to each other, or just inspection, right? I mean, it's okay to just look at it and get a lucky guess. Not a lucky guess, an educated guess. Just try something that looks like it makes sense. 1 here works, right? 1, we plug in 1 here, we get 1. We plug in 1 here, we get 1. Right? But you just need to know that if you couldn't plug in and get it, you need a way of doing it. So you'd set this equal to this, wouldn't you? You'd square both sides. Ooh. I think I like the inspection instead. In fact, if we did that, just so you could see, if we were to take these two and set them equal to each other and square both sides, you would have an 8th degree polynomial function or polynomial equation, and there would not be a way to solve that with any technique that you've ever learned. So it would have to be inspection. Or Newton's method from Cal 1, which that was a long time ago. So remember, Newton's method was a way of finding zeros of functions that uses an algorithm. And that's the way the computer does it. So, all right, good? We got it? Let's set up the integral. Integral from 0 to 1. The one on the right, root 2 minus y, right? Minus the one on the left, y to the fourth, dy. And then you go through and you integrate. Now this integration is going to be a little more involved because you have, well, this one's easy. Antiderivative y to the fourth is easy. This one, you're going to have to do a little basic u sub or something, but it'll work out. That's not trig sub or right? This is just a basic, maybe we should do it. I'm just going to do that one. I'm not going to do the other one because the other one's too easy.
2 minus y is u.
So let u be, 2 minus y. Du would be negative dy. And you're off by a constant. So this would become integral, pull the negative out, du root u. Right, that's root u. dy, negative, change it to positive, would be negative du, and then antiderivative of the square root of u is 2/3 u to the 3/2, and blah, blah, blah. Okay, so dot, dot, dot. Let you do that yourself. We okay? All right.
How, on that one,
Yes.
looking at the picture, how would you determine which one's the greater, which one's f of x?
The one on the right side.
I'm not getting.
Oh, you mean like from my drawing?
Yeah, like
Alternative.
just based on the drawing, like which one would, like, because I can't tell which one would be greater.
Well, when I drew this one, which one would be greater?
Well, like, because which one would you be subtracting which one? Because like I can't tell from the picture.
Okay, so when we draw the picture and we do it this way, and my rectangle goes like this,
Yeah,
it's obvious top and bottom, right?
right.
This one, you're just doing right minus left.
Oh, because it's horizontal.
That's right, right minus left. You're not looking top and bottom anymore.
So wait,
That's why I said turn your
Yeah,
head.
because I was like,
Yeah, if you turn your head, then you can do it.
I was like, wait, so.
Yeah, got it?
All right. Just turn your head.
Now, look, just a little side note here. You actually can do this problem. Remember how I switched all the y's and the x's? When I first started teaching Cal 2, that's what I used to tell my students, like, look, switch all the y's and the x's. Start a new problem over, and now you can use your calculator. And that's great. But the problem you run into is in Cal 3, you can't do that because you have x, y, and z, and you can't switch. You just can't switch variables. The reason you can switch it in Cal, like you could do it, is sacrificial paper. Here's why. There's our standard XY plane, right? Positive X direction is over here. Positive Y direction is over here, right? Okay, so I need another one. Just tear it out. I don't need the holes. If I come in here and I just, out of nowhere, I switch it, my X and Y, everywhere I see X and Y, I change to this. These two obviously would not be the same thing, would they?
Right.
But is there a way that I can turn this one into this one with just moving things around? So just watch this. If I turn this piece of paper over and rotate it. So if you look at this from the opposite side and you turn it 90 degrees, is it the same picture? Can you all see through the paper? The X and the Y are both in the same direction now. That process of flipping and rotating means that these two are what we call isomorphic. They're the same space, basically. So there's an isomorphism connecting these two spaces together. You cannot do the same thing for three-dimensional space. If in three-dimensional space we use standard, what we call right-hand rule, those of you who've taken physics, right-hand rule tells you something about the way the axes have to be oriented. Who's seen right-hand rule? Okay, so if someone comes in here and says, all right, I'm just going to switch my X and Y variables now, like that, your right-hand rule's gone. And there's no way to turn it or rotate it and do anything to make it match up right-hand rule. It's violated now. So since there's no way to do that, that's why I stopped doing it. That's why I stopped. When I first started teaching it, I was like, no, it's an isomorphism. Fine, we can just change it. Who cares? But in Cal 3, you can't, so then you're stuck. And then you're trying to deal with these things that are drawn sideways, and you're like, I never did that. And you're freaking out. And then you come back and blame me for it. So rightfully so. All right, what's next? There was our region. Boy. This is just an interesting one. X to the fourth, y is x to the fourth, y is x to the sixth. X is greater than or equal to 0. This is just because when you graph x to the fourth, We know x to the fourth looks like this. And x to the sixth is where? The same but steeper. So would you agree that they both hit the same place at 1 and -1? And you said it was steeper, right? So x to the sixth should be above x to the fourth? Like this? Should be above like that? What about between -1 and 1, though? Where is x to the fourth and x to the sixth? This is actually below x to the fourth. So I just want to make sure everyone's clear on that. A lot of people think, okay, x to the sixth is always bigger than x to the fourth. Always. That's not the case. If you take a number like 1/2, right? What's 1/2 to the sixth? Well, it gets smaller each time, right? 1/2 times half times half. That gets smaller. 1/2 to the fourth gets smaller, but this is more of them, right? More halves. So this is 1/2 to the sixth is actually not greater than 1/2 to the fourth. It's smaller. Once you get past 1, then yes, it's true. X to the sixth is bigger than x to the fourth. So on that problem right there, the region you're looking for, notice the condition x is also greater than or equal to 0, would be the region right here. And so what would your top function be? X to the fourth. So this is integral 0 to 1, 0 to 1. And then x to the fourth minus x to the sixth dx, and then whatever that is. That's just to, just so everyone's clear that, it's not always x to the sixth is bigger than x to the fourth. All right, let's talk about this one. Absolute value. So we have y is the absolute value of x. We have y equals x squared minus 2. And find the area of the region. So I've got to be able to get a good graph. Y'all comfortable with what the absolute value of x looks like?
Yes.
What does it look like? A V, sharp corner, like this. X squared minus 2, parabola, move down 2. Goes up. Eventually, it's going to hit this guy, right? This absolute value, eventually, it's going to pass through it. Whoa, wow. That's supposed to be symmetric. That good? That's it. Area of the region bounded by those. Do you all see the region?
Yes.
Yes. What would you like to do here? Find the what? Endpoints, which would be where, what, here and here?
Yeah.
Let's decide. If you're going to say endpoints, then I think you've decided already which way you want your rectangles to go. Vertical? You want to go vertical?
Yeah.
Wait, but you run into a problem though, right?
Where do you run into a problem?
At 0, 0. At that point, right? Because when you're making your rectangles vertical, you have to stop at that point.
Yeah, something's happening here, right? Like if I draw a rectangle here, it's the red and the blue, right?
Right.
But look, the red's slanted this way. And then when I come over here, this side, that's a different slant, isn't it?
Right.
What's that? Yeah, why does it matter? Well, you'll see. Let's stick with this. If you're going to try this, give me your intersection points. I think you're going to see in a second why.
Yeah, there's a really
Intersections. So set them equal to each other, right? Uh-oh. Yeah, how do you solve that equation? Uh-oh, this is a deeper question. How do you solve an absolute value equation?
Did you say the absolute value on both sides?
Close, it's something like, All right, let's back this up. Hold on, everyone. What if I tell you the absolute value of x is 2? What's x? 2 or negative 2, right? So if you ever have an absolute value equation like this, you have to actually set up two equations, don't you? One of them is just drop the absolute value, right? And just write down that, and that's it. The other one is drop the absolute value and change the other side to negative of what it was. So if I want to solve this equation, I actually need to solve two equations. The first one is just x equals x squared minus 2. What's the other equation?
X is negative x squared.
X is negative x squared plus 2. So one of them is just drop the absolute value, just do your business. The other one, drop the absolute value, change the signs of the other side. They're both quadratics. So what do you get here? X squared minus x minus 2 equals 0. So minus 2 plus 1 equals 0, and you get two answers, 2 and negative 1. Yeah? You have to check them. You need to check these answers. Does 2 work? What's 2 squared? 4 minus 2? 2. You're plugging 2 in here. Absolute value of 2 is 2. That works. How about negative 1, though? What's negative 1 squared? 1 minus 2? Negative 1? Negative 1 absolute value is 1. 1 does not equal negative 1. That does not work. So you have to check your solutions on absolute value equations like this. The other one, if you move things around here, x squared plus x minus 2 equals 0. You get x plus 2, x minus 1. And you check those, or get those two answers. You get negative 2 and positive 1 this time. Check it yourself. 1 doesn't work. Negative 2 does. So negative 2 and 2. Y'all still all right with that? All right. I'm still waiting to see if you see where we're going to run into a problem.
At the point. Is that at the point?
Where?
Or is that just for derivatives?
So, yeah, so look, yeah, that's for derivatives, yeah. Look, it's okay here because we still have a top function. The fact that it's 0 doesn't matter, okay? But something interesting is happening at 0. So let's try this. If you were going to try to go integral, I think you want me to do this now, right? Exactly. Let me show why we want to do that. What would your top function be here? Absolute value of x. Bottom function? X squared minus 2. What is wrong with that? What's the antiderivative of the absolute value of x? We haven't talked about that, have we? Well, we could, but
There's a formula.
there is a formula, but let's use the symmetry of the problem. Let's use think about what this is. If you're on this side, right, isn't this just x? Isn't that just x? Y equals x? And then on this side, isn't that negative x? Agreed? So this is something you should know. The absolute value, I'm not saying no like you should have known this coming in here, but when I show you this, maybe you've seen it before. The absolute value function is actually defined to be a piecewise function. It's x if x is greater than or equal to 0, and it's negative x if x is less than 0. That's what the absolute value function is. It's actually two functions put together. X, which is this one, as long as you're 0 or to the right of 0, and it's negative x if you're on this side. And just think about how this would work. If I plug in negative 4 into the absolute value, the first thing I would do is say, okay, is negative 4 bigger than 0? No, right? Is negative 4 less than 0? Yes. So plug negative 4 in right here. What's negative negative 4? Positive 4. So that function does exactly what the absolute value function needs to do. It leaves positives alone and it changes negatives to positives. So what we're going to do now instead of doing this integral, because that's a problem, is we're going to, even better than that, we're going to start at 0. We're going to go to 2. We're going to use the x here, and we're going to double the answer. Right? Because this is symmetric. So whatever area I get here, if I double it, I get the other side. So I'm going to use the symmetry of the problem to just go from 0 to 2, just working with this part, the red part here, as my top minus the bottom, still the parabola, and then double the answer. Got it? Okay.
It won't matter that it's below the x-axis.
Does not matter. Yeah, so what happens here is when your rectangle's down here, if you were to plug in a value in here, it would spit out a negative number, right? So your top number up here is positive. Your bottom number here is negative. And so you're doing a positive number minus a negative, which makes it a positive, so that gives you the greater length that you need for the height. So it's okay that it's below. Actually, it accounts for that in the formula. It's actually a good thing. All right. This one, sketch the region bounded by x is sine y, x is cosine y. I'm not going to go through this one. I just want to show you what the graphs are. This is basically the sine and cosine function. It's just the sine and cosine function drawn sideways. So if you were to go into the other room, go out this door, go into the other room, and look at that board and turn your head this way, you would see the sine curve, you would see the cosine curve, like this, right? That's what you would see. And then what you're trying to find is the area between here, 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 like that. I don't remember what the restrictions were. I think y had to be greater than or equal to 0, or y is 0 and y is 2 pi. So it would just be like 2 pi here and then 0. So what you would have to do this problem is split it into 3. You'd have to figure out where they hit each other. I'm going to offer that as a bonus question, just to be turned in next class. Okay? That's a bonus question to be turned in next class.
Professor, do we have access to that or no?
Yeah, right there. There it is.
I mean, outside of class or no?
I think it is. X is sine y, x is cosine y, y is 0, y is 2 pi. Every time that you do one of these, because there's 3, right? Your top and bottom switches, right? But in that picture, it's your left and right switch. All right, I have about 5 minutes. Okay, so y is e to the x. Y equals 2 e to the negative x plus 1. X is 2, and that's it. Those are the curves. That's it. We all know what e to the x looks like, I hope. That's e to the x. All right. What does e to the negative x look like? Reflection over which axes? No, y-axis.
Oh, yeah.
That's reflection over the y-axis. So it's this thing like that instead. What does multiplying by 2 do?
Compress it?
Taller, yeah, or you compress horizontally, stretch vertically, either way. Just makes it go up a little faster on the left side, right? What does plus 1 do? Shifts it up 1. Whole thing up 1. So when I graph, pardon me?
No, he's like left one, but it wasn't inside the parentheses whenever you have.
That's right. That if it were, it would have to actually be up here to move it left or right. So it should look like this. It's went down too far. This one has a horizontal asymptote at 0, y equals 0, out the left side. That's what e to the x does, right? If I lift it up 1, then on the green one, then the horizontal comes up 1. That's not that important to us because we're not going to need that. What about x is 2? Vertical line at 2? So
basically it'd be the point.
I'm guessing it's out here. I'm guessing it goes up like this. I don't know. What if 2 is to the left? I don't know where these hit, do I? Not yet. I'm about to. That's going to be my guess. I think this is the region. I'm pretty sure we're looking for that. In which case, I would want to do vertical rectangles. Y'all follow me?
Yes.
Okay. I would want to do vertical rectangles. It looks like I know what my right endpoint would be. I just need to know what my left endpoint would be. How do I get my left endpoint? Set them equal to each other. So I'm going to set e to the x equal to 2e to the negative x plus 1. Drum roll. How do you solve that? And the log might come into play here at some point. Not quite yet, though. Only because the right side's a mess. If I do the log on the left side, everything's good. But the log on the right side's not good. What's that?
Could you put them on one side and take out
You could put them on one side, take out an e to the x. If they all had an e to the x, the one doesn't. Anyone have any ideas? What? Skip it? Is that what you said?
Sorry, don't skip it, you circle that one.
Maybe that will help.
Okay.
Does that help?
Yes.
Okay. How? What could you do here?
You can leave it as 1 over e to the x.
Mhm.
The 2 and the
Move the 2 over.
Oh yeah, e to the x. over
Move
e to the
it.
x.
Move it. Yes, I'm hearing the right kind of trend idea, but I'm waiting to hear one specific thing. I mean, all the things you're saying are algebraically I could do, but I'm not quite sure any of them get you where you want to go.
You could just plug into
What don't you like there?
that's in the
The
denominator.
e to the x on the bottom, right?
Yeah.
There you go. Clear the fractions. Multiply everything by e to the x. Did you say that?
I said multiply on each side.
By e to the x? Did you? Okay, then I didn't hear it. Well, you weren't very confident when you said it because I didn't hear it. Okay, so look, you're going to multiply both sides of the equation by e to the x. This will have the effect of clearing out the fraction. So multiply e to the x here, e to the x here. So when you distribute this through, what's going to happen? What's on the left side?
2.
E to the 2x. Remember, e to the x times e to the x, you add the exponents, x plus x is 2x. Okay, equals, when you distribute here to here, the e to the x cancels, 2 plus 1 times e to the x. Okay, so it's no longer a fraction. That could be a quadratic. If we move everything to one side now, and I'm going to put it in this order. Then you could look at that as being e to the x squared minus e to the x minus 2 equals 0. And in college algebra, we call this a quadratic form equation, like a u substitution, but not the u sub that we do in this class. It's just everywhere I see e to the x, I'm going to replace it with u. And then this problem becomes u squared minus u minus 2 equals 0, which means u minus 2 times u plus 1 equals 0, which means u is 2 or u is negative 1. Now what was u? E to the x. So e to the x must be 2 or e to the x must be negative 1. We won't be able to do that, but let's verify. Now log. Now log. Natural log of e to the x equals natural log 2. So you do that on both sides. The left side, you just have x. The right side, natural log 2. Over here, you could do it again. Natural log e to the x equals natural log of negative 1. You cannot do natural log of negative 1. So your only solution is x is natural log 2. Oh, so that's where they hit each other. Natural log 2. So then you set up your integral. I know I'm out of time. I don't keep you all over very often, but I'm going to finish this. Integral is going to go from where? Is natural log of 2 smaller than 2? Yes. Yes. Okay, so natural log 2 to 2. What's the top curve? E to the x minus what's the bottom curve? 2e to the negative x plus 1, and then you'll distribute the negative through, won't you? Yes. And that should be easy to integrate. Antiderivative e to the x, you should be able to do. That you should be able to do. Then you plug in 2, you plug in natural log 2. What happens when you plug in, like, what is e to the natural log 2?
2.
That's just 2. So that should be pretty clean also. All right, we're out of time. Next time, we start taking these. I think the homework's at the end here. Sorry, there it is. Next class, we start taking these regions and start rotating them around the axes and getting volumes. Yep, that's where things get fun. Have a good rest of your day.
Will we ever learn, like, natural log of a negative number? Is that possible? With imaginary, maybe?
Yes.